All right, this chapter is about reactions with aromatic compounds. All right, so last chapter was about what is aromatic, what makes something aromatic. This chapter now is going to be about what reactions can you do with aromatic compounds. Most of the reactions we're going to talk about are what's called an electrophilic aromatic substitution. So we're going to be substituting one of the hydrogens on the aromatic ring with an electrophile. So in this case, this hydrogen right here is going to be substituted for some sort of an electrophile. Okay. Now, one of the things about doing reactions with aromatic compounds is that you have to break up the aromatic part of the aromatic ring, which you can imagine is not very stable, because the whole point of compounds being aromatic is it stabilizes the compound drastically. So you're going from a compound that's aromatic, you're forcing it to not be aromatic anymore, which is what this sigma complex means. Okay, and then you're reforming the aromatic part of the compound, all right, by plucking off that hydrogen. So this complex or structure, intermediate if you will, is called a sigma complex, and you're going to see this over and over again, and it's just the name of going from an aromatic compound to a non-aromatic compound with the electrophile going back to the aromatic compound. Okay. So although benzene's pi electrons are in a stable aromatic system, they are available to attack a strong electrophile to give a carbocation. Okay. Now, in order for the aromatic ring to break apart, this electrophile has to be very reactive. Okay. If this is not reactive, we got to make this reactive so that we can lower that activation energy for reaction. Okay, this resonance stabilized carbocation is called a sigma complex because the electrophile is joined to the benzene ring by a new sigma bond. So again, your plus charge in here, and we're going to see all the resonance structures, but the plus charge is resonance stabilized. And then eventually aromaticity is regained by the loss of that proton. That's why it's a substitution. You're substituting this hydrogen for an electrophile. You're not adding to it. It's not an addition. An addition implies you stop basically at this molecule, but we don't. We reform the aromatic compound. Okay, so here's a general mechanism showing the sigma complex. Okay, so the first step is the attack on the electrophile to form the sigma complex. So one of the pi bonds is going to share its electrons with the electrophile. Okay, so if the electrophile goes here, all right, you're going to form a plus charge on this carbon, as you can see here. And then through resonance, you're stabilized. So these pi electrons will go to here to give you this sigma complex, and then these pi electrons can go here in another resonance structure to give you that one. Okay, and then eventually, so even though you're breaking up the aromatic part of the ring, you're still forming a resonance compound. But notice from last chapter, all right, we're not really, this compound's not aromatic. All right, we no longer, you have an sp3 carbon, but it's stabilized through the resonance. And then eventually, what the second step is you have some base come in, pluck off the hydrogen, and reform that pi bond. So it reforms the aromatic part. Okay, so 7.2 is just kind of review and just kind of to show you that you can't do a regular reaction on an aromatic ring. So we saw this last chapter. If you take Br2 and just add it to a double bond, you get the dibromo compound. Well, that does not work. Okay, it takes plus 8 kilojoules. Now, that might not mean anything to you, but I'm telling you, that's a lot. Okay. However, what you can do is you can take a bromine with a Lewis acid catalyst. All right. In most of these reactions, we're going to be adding some sort of catalyst to it, because again, you have to activate your electrophile somehow to bring the activation energy is equal enough to do a reaction. And notice you are substituting one of the hydrogens. Notice now the reaction is -48, so it's exothermic. It's actually going to a more stable molecule. So that's kind of the driving force for the reaction. So let's talk about that mechanism of that reaction. The first step is the activation of the bromine with the catalyst. Okay? And what happens is one of the lone pairs of the bromine attacks your iron to form this complex or intermediate. Okay? This bromine right here now becomes very, very electrophilic. You would think it's this one because of the plus charge, but you can't really attack that because it has two bonds. It's this bromine right here. All right, that's the bromine that your aromatic compound is going to attack. That becomes very electrophilic. Okay, so just to kind of reiterate, before the electrophilic aromatic substitution can take place, the electrophile must be activated. Okay, a strong Lewis acid catalyst such as FeBr3 should be used. Okay, so here we go with the mechanism. So once you have the activated complex or catalyst, okay, or your bromine is activated, okay, now you have the activation energy is not so high. You now can break up your aromatic compound. So the pi bond now attacks the bromine, breaks off your catalyst as FeBr4 with a negative charge, notice right there, to form your sigma complex. You now have the resonance of the carbocation. The next step now, as you saw in the previous slide, is now a base is going to come by and pluck off the hydrogen to reform the aromatic compound. Your base actually happens to be the catalyst. Okay, so your base comes by, plucks it off, reforms the aromatic compound, and you just brominated your compound. Plus you form HBr. What ends up happening is that the bromine, this extra bromine, kind of bonds to the hydrogen and then breaks off of your iron. So you reform your catalyst. As you know, what makes a catalyst is it gets reformed. You can do the same reaction with chlorine, but the catalyst now is aluminum trichloride rather than iron trichloride. You use aluminum. Okay, chlorination is similar, but AlCl3 is most often used. But you can use iron trichloride. Aluminum chloride is like the king of Lewis acids, Lewis acid catalysts. Okay, if I was going to do a reaction and I didn't even know what catalyst to use, I would just use the aluminum form of the catalyst. They really are. Aluminum is an exceptional metal. It's used quite a bit as catalysts in organic chemistry. But you can use the iron trichloride. The next reaction we're going to talk about, so that's halogenation. The next reaction is nitration. Okay, putting on nitro groups. Now your catalyst in this case is a strong acid. This is your catalyst. Okay, you have a strong acid catalyst. Okay, and usually it's sulfuric acid. Right, this mixture, this nitric acid and sulfuric acid mixture is a really, really strong mixture. Okay, it's an incredibly strong acid. It basically it does a lot, and it can actually eat through a lot of things. All right, but this is how you nitrate aromatic compounds. Okay, sulfuric acid is the catalyst, allowing it to go faster and at lower temperatures. A lot of these reactions, a lot of the aromatic reactions occur at very high temperatures. They react together to form the electrophile, the nitronium ion, which is this NO2+. This is a very, very active compound. Again, this is not reactive. Okay, in order for a reaction to occur, there's nothing I can do about this, but this I can change and alter. And trying to make this reagent so reactive, it forces the aromatic ring to actually do a reaction. So this is the first step in formation the nitronium ion. Okay, the OH group on the nitric acid protonates from, the OH group of nitric acid. Right, this is nitric acid, HNO3. I'm going to write it as this, HONO2. Sometimes it's easier to see that. Plus my strong acid. I'm going to kind of show the same thing, but a little bit easier. Protonates to form this compound, which we've learned that water is a very good leaving group. Okay, so what's going to happen is the water is going to leave to form water and NO2, your nitronium ion plus water. Okay, once you get the nitronium, that's when the reaction occurs. That's when the sigma complex is able to form. So here it is, your aromatic compound attacks the nitronium ion, kicks up the lone pairs to put the nitro group on your ring. Okay, here's the sigma complex resonance structures. The sulfuric acid or water, whichever one you want, will come and pluck off that hydrogen, reform your aromatic compound. You just nitrated your benzene ring. Okay. Now, nitro groups, not a lot of compounds have nitro groups on them. Nitro groups are good at making explosives. All right, we learned, I believe, last chapter that TNT, trinitrotoluene, is this compound. Is you have a CH3, your toluene group, and then 3 NO2s around your ring. That's TNT. Okay. Well, you can imagine how to make this. You start with toluene, and then you just add nitric and sulfuric acid and 3 equivalents and put 3 nitro groups on your aromatic ring. That's basically how you make it. However, this is pretty good for exploding things. It's, I believe, also no, I'm sorry. Yeah, it's used as an explosive. All right. Well, nitro groups aren't that useful unless you're going to explode them. But what if you don't want to explode them? What if you want to use it as something? Well, amino groups, or aniline, remember this is called an aniline group, all right, is a very useful compound. It's found in nature. It's found in a lot of different, it's found in a few of our amino acids. These aniline groups are very commonly used. However, you can't easily put an NH2 group on an aromatic ring. Okay, it's hard to attach an NH2 directly on an aromatic ring, but you can easily put an NO2 group on. So there's a reaction which fortunately reduces the NO2. It can take an NO2 and reduces it. Remember, reduction means remove oxygens and add hydrogens. Okay, and the reaction is either adding zinc or tin or iron in the presence of HCl. It's a very simple reaction. I've done it before. You just basically throw in like zinc metal and hydrochloric acid, and you can change it into the amino group. Okay, so treatment with zinc, tin, or iron and dilute acid will reduce the nitro to an amino group. This is the best method to adding an amino group to the ring. Like I said, it's very difficult to just add an NH2 group.